concepts uh, appeared in modern science in 17th century, which I will show. When there is a dark, when there is a night here, it's a day on the other side, and sun does not really rise or sink. Okay. Next thing, the earth with its mountains, trees, oceans, being is nothing but an atom fixed on the hood of Ananta, infinity. So earth itself was considered as just an atom is in infinite universe actually. So earth was considered just. So later on people realized that people scientists struggle to prove this point actually, and I will note that the modern scientists struggle to prove these 2 points. In fact, they died actually. They sacrificed their life in till 17th century. The scientist fraternity gave up their life to prove these points. So these are some of my students who contributed to my work at NCL in last 20 years. So so now question arises. So do you see this any floating window or you don't see? Uh, I hope you don't see any floating window, which I see on my screen. Anyway, um, so now question arises that when and why did ancient civilizations start looking for deeper questions beyond day-to-day survival? What brought this change in psyche? These are 2 3 slides from my talks which I gave in last 2 years at Science Day, 28th February. The last year it was at in Mumbai, South Mumbai, the Institute of Science, and this year it was hosted by Symbiosis Institute of Technology in Pune. So it was full-fledged talk, but I have taken only a couple of slides. So now question arises that when we started doing science actually, so again, this verse caught my attention where the Rishi said that there are endless transformations to the material qualities, right? Material qualities can have, and we know as a physicist, as chemist and biologist, and even though not even a person living as long as Brahma's age is capable of putting it into the words or fully understand it, I nevertheless say try to explain the in terms of name and form. So you can't. Sometimes knowledge is so abstract that you can't explain it in the words. And so when from where this unmanifest word came into the manifestation, how universe came into the existence. Bhugolakam, basically the earth is the round earth actually, not the flat earth, which people struggle to scientists struggle to prove as late as 17th century. Um, so this scientific temperament was there actually, and I will point it out. Uh, Earlier we had this life of hunter-gatherers. We were all tribes, part of tribes, and then we used to live in forest. And some people decided to have a hybrid way of life. End of the nomadic life, they started doing domestication of cattle, seasonal farming. Then they had excess time and calories. The belly was full. They settled along the rivers. So most of the ancient civilizations are across the rivers where there was a plenty of food available. So when they had food available, then they started looking at beyond the food actually and hunting their next meal beyond the survival. So then the science started when they started looking at bigger problems. Uh, right, and then they had plenty of time to think because their granaries was full with grains, seasonal crop. So this agrarian societies started doing earliest they were earliest scientists and mathematicians. They built complex city dwellings. We know the Saraswati Valley civilizations. The lot of proofs are available now. Comparison with their distant forest, some people chose to still live in the nomadic life, and then they created some social disparity which we still see today. The early development of the complex mathematics, metallurgy, town planning, weights and measurements, astronomy, abstract philosophies such as Vedanta around consciousness developed, and there are a lot of text one can refer to. Um, So further division of labor happened because the society became more complex. So the division of labor happened, and then super specialization happened, where families basically generations they build the skills. Actually, skill development was there. So somebody was from generations were skilled in masonry, somebody was doing weaving and art and craft. Uh, Now we have all lost all those things. So this was not limited to modern day India, but it was all across major river system in in Americas and Africa and some part of the world. Um, and they were all connected actually. A surprising thing is a lot of revelations are coming now that they were all connected. They were not like isolated as we thought. So they were like origins of pagan beliefs. They were all nature worshippers. So then came around like 2000, fast forward 2000 years from now, then came the arrival of one god one book concept and blasphemy, and where people will be beheaded for questioning that book, questioning that concept. So that was the death of questioning and reasoning, because people were afraid of asking questions. And this started from the Middle Eastern one god one book concept. So there is a famous saying that you have to be afraid of the people who just follow, they have only one book in the library, um, because they will only believe, they will close their brain actually, and they will kill anybody else who questions the book actually. So then it was an origin of more rigid form of religions and dark ages for science actually. So all the pagan nature worshippers were they all they all conflict converted into the rigid form of that was a decline. Somehow India and China they survived actually, and all these things are documented in two books. One mathematician in Cambridge, Dr. Bhaskar Kambale, and by Professor Mitchell Dunn, a French scientist. Uh, and there are more books by Professor Subhash Kak, and you can read detail. I will. So there, many people ask, what is the are religion and science mutually exclusive? Not at all. If you're religious, then you can't be scientist. It did not come from Sanatan Dharmic civilization, the pagan civilizations, because they were studying nature. They were in the awe of the powers of nature actually. Then came dark age of science, when open discussion and scientific temperament was hated for almost 1700 years. That came from uh, civilizations which followed one book. And then scientists started fighting in modern ages. The blasphemy, the example of Copernicus and Galileo, and dozens of scientists were actually burnt alive in Europe, but not in India actually. So now fast forward actually that so then the compounding of so now what is the future actually? Then so there was a less democratization of the knowledge, because knowledge was concentrated in one part of the world. I'll, so then 19th century BC, uh, many philosophers and scientists believe that Udalaka Aruni was the first primitive physicist in the recorded history. And so there are books written by a famous communist philosopher Devi Prasad Chattopadhyay, who basically everybody, there are other scientists who believe that his philosophy was earliest shoot of knowledge. He basically he basically proposed the theory of atomism. And you can find this thing in Jain literature also, theory of atomism, where particles too small to be seen as mass together into substances, an object experience known as kana actually, like karna actually, right? And fast forward, then came this philosopher Kanad, Rishi Kanad, and you can see an auditorium dedicated to Rishi Kanad. He basically was the first person who basically gave laws of motion. And why physicists ignored this? Because physicists did not know Sanskrit, and Sanskrit scholar did not understand what he had written actually. So one should, I would encourage everybody to study the Kana Sutra, and where he had really. So what he wrote at that time, that every Kanad basically is the name is atom eater. Kanad basically the atom eater. The name itself was so every object of creation is made of atoms. That is coming from his book actually, that Parmanu, which in turn connect with each other to form molecules. Anu. Atoms are eternal and their combinations constitute the empirical material world. Kanada mentions several other natural phenomena. I can't go into detail, but I will encourage you to read this. The and you can relate it to the electromagnetic theory and gravitational laws, like laws of intermolecular forces. The falling of objects to ground, rise of fire upwards, why the candle fire or fire, the flame rise upwards, the growth of the grass upwards itself, the nature of rainfall and thunderstorm, the flow of liquids, the movement towards a magnet, among many others. He then attempted to integrate his observation into with his theory. So, and this slide I've taken from Mitchell Danino, that India's love affair with infinity. So they were looking at the very small dimensions, 70 nanometer, and the time scales and the weight mass scale, like milligram, like I would say that microgram, and then microseconds. So what were they doing actually with these units and symbols? And there is a famous book by a retired NPL scientist, Professor SB Gupta, and second edition has also come. So I will encourage you to read there. I will skip it. So now coming fast forward in 17th century, the classical cracks started appearing. The cracks in the knowledge started, and that was the birth of the quantum age. Now, arrival of 17th century, birth of alchemy. They were all alchemists actually, and then astrology, and that finally paved way to the modern versions of chemistry, physics. And I will say what were the problems, and be ready for a really exciting journey now. So I will mention three names here. Robert Boyle, right? He was again Irish person, and the famous gas law. And just remember these names and their invention. And Newton actually. Now let us start the slide. Next slide. So what happened in now I'm actually, my slides are chronologically arranged, so it will be very easy for you to follow. So make mental notes of uh, all these slides, at least the titles of these titles actually, and the year. Okay, so that will help you to chronologically correlate these events and their problems and the solution, and how we arrived at the present time. So 1687, after the book, then Isaac Newton's book Principia arrived, then the scientists at that time were so overconfident, that was noted as classical overconfidence and euphoria created by the publication of this book. And people thought that classical mechanics is capable of describing everything in the universe, because you had these laws of motion, and once you know the trajectory, people thought that I can go backwards and forward in time, and I have a clear and deterministic view of the entire universe. So so they thought that future can be predicted, and past can also be known. So that was a chilling mechanistic claims. Even the famous scientist Laplace, he was a French scientist, he was considered as a Newton of France. He made his famous claim that if you have the unlimited calculating power, and with the complex knowledge of all particles, at some instant of time, you can actually predict, using the Newton's equation, you can predict the future. And also a very bold statement that retrodict with the equal certainty of the past of the whole universe. That was the confidence. And Newton himself got so overconfident that using his equations, he predicted the end of the world. He gave the date of the end of the world. And Newton's date of the end of the world has already expired, actually. He it's already passed, so it did not come. And so Newton did not, and also Newton did not suddenly invented laws of gravity after Apple hit on his head. So the knowledge had been incrementally compounding over thousands of years. Don't forget the Rishi Kanada's contribution, which these texts, Sanskrit texts, were reached to Europe through missionaries. Okay, and then they were translated, and then it reached to the hands of that time's scientist, and that was a compounding of the knowledge. It was not like eureka moment. I mean, science does not happen. Serendipity is extremely rare. I mean, that you have, you have apple hitting on your head. I mean, you can retrospectively, that you can create stories. But anyway, so 19 so there were more problems, that are humans merely clockwork automata? Are we machines, that humans? But because our the daily experiences in life do not suggest, we know that everything is all events of our lives are driven by uncertainties, right? We can't, where what we are doing today, could we predict, could we predicted even 15 days back, or 1 week back? No, we could not predict most of these events. Look at the Trump tariffs and all kinds of things which are, could you predict 2 years back, 3 years back, and even 6 months back? So Newton himself had declined. So he gave these laws of motion, the inverse square law of gravity. But the problem was that with the classical physics, that there was no mechanism. He did not give any mechanism. It was just a hypothesis actually. And another second thing, nature of light. So that also he gave this particle concept to the light. We know that that light is made of corpuscles, and but then there was no uh, there was no there was no mechanism behind that. So it was like, I mean, that was early sign of science of European accepting the theory of atomism, which originally was already there in the Sanskrit literature. So then there was a fight started between Boyle versus Newton. They were all giants of that time. So because Boyle says that intermolecular forces are repulsive, and Newton says that there is always only attraction. So are these future are these forces oscillatory in nature? So that was very so apparent contradictions. So there were big contradictions in 17th century, and very heated debates, actually heated controversy in scientific conferences, that sort of many seeds there were let, okay. So it took I will just show that it took quantum theory, quantum mechanics to solve these. We'll discuss it later. So then came 18th century. That was the age of lot of confusion, contradiction, and controversies in the science. And it's always good. So a lot of churning was happening in the scientific world. um, uh, so then confusion over the idea of action at a distance with no intervening substances. So people were making fun of the scientists, that how two molecules can feel each other from distance. Is there any, I mean, how, what is the transaction? Is there any transactional? How do they communicate with each other? How Earth and Moon know each other's, or how other planets they know each other's present? Is there any exchange of information? I mean, is there any exchange? How would they know? I mean, now we know, now we have little information about gravitational waves and other things. So also that was a long range, but short range also, between molecules. How do they come together and combine? Even the molecular theories were doubted actually. So that was the age. So notion of a general oscillatory force between all particles was not was very puzzling scientist. And then came early 19th century. Then another problem came actually, that emergence of conflicting theories about, I was talking about, last slide was on the origin of forces, but now I'm coming to the nature of light. And this controversy was started by Thomas Young in 1801, very early 19th century, the beginning of the 19th century, in fact. So he that he gave his single slit experiment, and then he thought he showed that there are these fringes, actually famously bright and dark. So interference phenomena was seen by the world. And there were many other people who contributed to this wave theory 19th century. There are many, actually, Fresnel and Herschel, and famous Airy, no, the we teach George Biddle, Airy disk wala Airy, right? Okay. And then we knew the diffraction, limit of diffraction, the okay, that was also around the same time, Rayleigh's diffraction limit, and also okay, so that lambda by 2. Okay, so this also Newton's ring, don't forget, so this was, so wave theory was becoming more popular rather than the particle concept which Newton has had proposed to the light. um, so then there were conflicting theories about electricity and magnetism. There were a lot of experiments which were compiled together by famous equations of Maxwell, and it was one of the greatest invention of 19th century. And but the problem with the Maxwell was that he could not avoid the temptation of uh, uh, using this mysterious, all-pervading medium as ether. The problem with the ether. So all his theories, and not just his theories, but till his generation, ether was part of all scientific theories. So 18, just 15 years later, 14 years later, so there was the death of the ether. There was no need for this concept, thanks to the Michael Morley's famous experiment, and then later on with the spatial theory of relativity, which could explain that there was no need for ether to take into the consideration. In 19th century itself, there was a lot of problems going on in scientific world, continuum versus molecular theories. So people first after the 19th century saw the continuation of the controversy, where the matter was the debate was whether the matter is a continuum or made of molecule. Now you retrospectively you may think that it I mean, oh, what kind of debates they were having, because we take the scientific inventions for granted. So now you can say that, okay, why were they? I mean, so that was a debate for almost two centuries actually. That molecular theories, like matter is made of atom, and fast. When we go back to the Jane text, actually, the atomic. That they already had given that the Jain philosophers, that the matter is not continuum. It is made of kanas and the atoms and anus and parmanus, and those anu parmanu concept was already there actually in 7,000 years, probably 8,000 years earlier. So the continuum theory won surprisingly, and the death of molecules in 19th century. It's surprising to you. It may shock you now actually that uh, so the belief in the molecules declined actually, and Maxwell famously said that the main reason that by mid-century, mid 19th century, no one believed in molecules any longer was not because of anybody had shown that they did not exist, but because all those who believed in molecules are now dead actually. So it was a very funny statement. So you can see that how you need to have long life to survive actually the this to see the uh, new theories actually, that comes the age of immortality. So then later half of the 19th century saw the return of molecules. uh, okay, so thanks to the success of new kinetic theory, and then we'll come to that van der Waals equation of state. Both required actually the attracting molecules to explain them actually. Then there was a birth of classical statistical mechanics and unification of quantum theory. We know the Maxwell-Boltzmann statistical statistics, and then that gave a lot of that basically did a lot of good actually for the homogenization of these two theories. But there was but however, Word eagerly waited for a radical new theory for radical consolidation, because still the origin of forces we did not understand till 19th century. Nobody, there were these were just speculations, because we did not understand. So Word waited for till I think we are running 100 years. 1925. So in 1920s, actually, there was these things started rapidly clearing up when the advent of modern quantum theory started. So, in the late 19th century, the first phenomenological theory of intermolecular forces, you know, that it was given by Van der Waal force, Van der Waals, that famously known as Van der Waal force. So he said that he did not that, but there were a lot of problems in his uh, his uh, his theory. The first problem is that he took only attractive forces in consideration. So that did not explain the repulsive nature with Boyle had observed PV is equal to RT. He did not explain the repulsive forces at a shorter distance. And sadly, he died actually. The Van der Waals died actually in 1923 at the time when quantum physics was just taking birth. Had he lived for 5 6 more years, he would have seen the quantum mechanical origin of what he had proposed. However, he got Nobel Prize in 1920. So non-ideal gases taught us the general truth, electrically neutral bodies, and also his theories were only applicable to neutral molecules, not the collection of molecules, not the macro molecules, not the macro world. We know that. So a lot of two, three theories had to come in. I will speak only one of them. Then finally DLVO theory came, and that included the charges on the molecules that considered the charge. Now that was the birth of the modern electrochemistry and other things. Okay, and where we when we started considering the charge on the neutral bodies, and Hamaker's famous contribution where he could integrate the intermolecular forces, and then we could apply the modified van der Waals force by integrating them over thousands of molecules. So we could apply them to the real life the nanoparticle systems and stuff like that. Otherwise, van der Waals theory itself was not of much practical use actually. So practicality was completely missing. This formula you already know. I'll skip it. So so but this concept was the physics was missing. That what is the origin of this glue between atoms and molecules, especially the neutral the non-polar molecules. Then the quantum mechanics itself gave this answer, the dance of charges. Much later, after the death of van der Waal, I'm actually fast forwarding it. The advent of quantum physics only told us that in all matters there are continuous jostling of positive negative charges. So there is a quantum fluctuation, then quantum mechanical uncertainty that give rise to this glue, the bond, or the intermolecular attractive forces, and also thermal agitation prevents it and also helps it, because the electron cloud around the cloud around, because see, there was no concept of electrons by that time. Please note that, the we did not have the the modern atomic model. We did not have any of these things. So nobody knew, people were struggling to have even the concept of molecules in place. So forget about anything else. So we basically, when I also made these slides, so it did not sound very I mean, what's going on? I mean, I was thinking that what's going on. It's now we take it for granted. We think things are like part of our life. Now these are, because thanks to the quantum physics, the things which we take for granted, people were struggling to to understand those things actually. Then the big scientists, actually, they were not like small names. Forget about the common masses. So the dance of charges basically gave rise to okay. So then we could understand that why gases, they liquefy, and then liquids, they solidified. The phase transition could understand. So the quantum physics basically could explain us the phase transitions, and obviously aided by statistical mechanics and the thermodynamics and other things. They all came together. So now we know that, I mean, these are the fruits of the quantum physics. But okay, that we now know that the Keesom force, Debye induction force, and most importantly, the London dispersion law, one of the most important, I would say, discovery, because that was the most important thing. The because London dispersion law was path breaking, which could explain between neutral, for example, liquefaction of helium and oxygen, nitrogen. Okay, so that could, now then we could we could see these forces, using atomic force microscope, which developed much later, in late 20th century, in around 1980s. We had full-fledged atomic force microscope where we could really see these things in real life. We could feel the forces actually. We could quantify, not just qualitative understanding was there, but quantitatively we could uh, we could see the forces actually. We could, okay. But then this Leonard Jones was the first uh, person, first physicist in Bristol University in UK, who actually combined repulsive and attractive terms. And so we know this famous formula of the me. So the precursor to the Leonard Jones famous equation was me theory. The same Gustav Me, a German scientist who gave the me scattering wala me. So he gave this 612 law, but again there was no physical explanation given by Leonard Jones. But when we take derivative of this, then we have this the red curve, which gives us the intermolecular force, repulsive and attractive here, and no force when the intermolecules are far apart. So this x-axis is basically the intermolecular separation, and then y-axis you have plotted potential in electron volt, and then force in nanonewton, or sometimes you can go down to piconewton. And if you cool it into the liquid helium, then uh, you can go much lower. So it was quantum mechanics actually which provided us the scientific basis of these both the terms. So 1 over r to the power 12 was given by explained by the Pauli exclusion principle, when the electron clouds, the concept of touch actually I explain in my classes at NCL. So which came actually, which was just, so they are not just numbers actually, there was scientific basis for that. Otherwise they just become mathematical equations. Nobody knows actually from where they suddenly dropped into our head and we have to cram it. So no longer quantum mechanics gave us power that no longer we need to just cram these long equations. We had scientific understanding actually, that solid foundation. Same with the 1 over r to the power 6, we had the solid foundation given by Keesum London D by. More importantly, London, I consider London's contribution as amazing. Now, 19th century was ending with the Lord Kelvin's giant old man of UK. He was Lord of Kelvin actually. His real name was something else. I forgot his real name, but that was not his real name. So he was so pessimistic, the like many of the old people like me sometimes. So that he said that all big ideas of physics are now known, and there is nothing new to do, and we need to just brush up those tiny details and with increased accuracy. So that time Max Planck, the young man, was entering into science. Many students listening to this talk, and he was advised that you should not enter into the physics because everything is discovered. Physics is now dead subject. Can you believe it? And there is nothing else which is left to do. But the young Max Planck fortunately ignored this advice given by people like Lord Kelvin and many others actually. And he won Nobel Prize, and he was one of the founders actually of the quantum theory 1918. So no one now, no, the lesson is that no one can predict the future with certainty, because the law of uncertainty seem to apply everywhere in the universe. um, and then now 1885, there was another problem. The the teacher, Swiss schoolmaster, school teacher, he was doing the recording the spectrum of hydrogen, and then he saw that there are these sharp lines. Now we know that Balmer lines or Balmer series. So that was biggest shock, one of the biggest shock, that was one of the first hint of the quantum revolution. And the spectroscopy gave, and people put it together, and then they found that there is some kind of equation which is fitting, and Rydberg modified it, but nobody really knew, because we did not have the concept of the modern day atom, the discreteness, the quantization of energy levels, nothing existed. So it was just one equation, which, so nobody really looked at the Balmer's, nobody took Balmer seriously. Another problem was that the plum pudding model, which was given by the giant J.J. Thomson, which failed to explain Balmer line. So this Balmer line was not at all compatible with the. So there was a big issue in the physics world, that what is going on. I mean, there were a lot of remember my slide, actually, the conflict, controversies, and all this. Okay, that was still going on. There were a lot of confusion, actually. Okay, so so plum pudding model was the only model which we had, and then it did not fit what was seen experimentally. Then also Lord Rayleigh, he highlighted that we are reaching to, in 1900, actually, around the same time, 3 years later. Lord Rayleigh, actually, he highlighted that we are reaching to the what he called ultraviolet catastrophe, because if we follow the Maxwell-Boltzmann statistics, then we know that all energy will pile up around the higher frequency domain, and that did not make sense, actually. That so if you increase the frequency, then you will have more piling of in the black body radiation, which was not the case. So that was famously named as ultraviolet catastrophe. Ultraviolet being the because remember that time we knew only till ultraviolet. X-rays were not discovered, actually. So you might wondering, why not X-ray catastrophe, because X-rays have lower, but then no, we did not have that, actually. Then 1 year later, Max Planck rescued the world out of this catastrophe. He gave that quantization of energy, the concept of photon, that really, then he told one fine morning to his son that he believed that he has made a great discovery. And he's told that it may be as significant as that of Newton. And Planck was daring, he was bold enough to make a contrarian proposal to all the seniors, giants in the science that time, that radiation was not a continuum, but it was made of these small packets of energy, which are related to the frequency of the radiation. That immediately actually solved this Balmer line concept, and to some extent until the Bohr's contribution came. So that was the first shoot of the quantum physics as of we know. Then came the final another contribution, again by giant Albert Einstein. We know, everybody knows about photoelectric effect. So that basically shows that we can look at the emission of energy from the any heated body, or later on the field uh, the field emission, actually, theory, whatever. So it is related. So we could see that that it is related to the frequency rather than intensity. Right. So the young Einstein had solved some of these puzzles, but there was another invention which really put scientists into doom. They were, so it created bigger mess. So now 1911, Rutherford experiment basically demolished the plum pudding model, and it indicated that no, not at all. Atomic structure is not like, you have the negative charge like plums into the positive charge, not at all. So they basically they say that, okay, positive charge is concentrated in a tiny space, which they call nucleus. But okay, they gave their model, but they left bigger problem, actually. So after this, so discovery of nucleus plunged all the classical physics into the deepest crisis classical physics had ever, because then the very stability of atom became question mark. how the classical physics will be able to, look at the giants of like Newtons and all these people. They were all demolished actually. Their whole model was demolished. So that was the biggest crisis, and it continued. And then X-rays, we know that X-ray diffraction was reported by von Levy, and then later on by Bragg father and son duo. That basically consolidated the wave nature of the electromagnetic energy. Yes. So, 1913, young the Danish guy, it's named, like Niels Bohr, he came to rescue. So he proposed a daring, a radical new hypothesis. So he basically told the world that the electrons can take discrete energy states and only specific values, and then he used the Planck's constant, and based on the angular momentum, the famous Bohr's model. But his model was actually based on geometrical optics. Not his model, sorry. Then we know, we teach this actually Henry Moseley's contribution was immense. So around that time, a lot of elements were being discovered, and we had some idea of periodic table. But periodic table itself was in a big mass. Actually, Mendelev's periodic table, because we were looking at the atomic mass. But then one experiment overnight by young physicist Henry Moseley. So what he drew a curve. So because we already had invention of X-rays, so what he was doing, he was measuring the X-ray spectra from different elements, and he was plotting the frequency on one scale, and then square root of atomic number, and he saw that logarithmically it draws this. He drew straight line. So, and then he basically he arranged the elements, instead of atomic mass, he arranged in that order atomic number. Then one night, actually, entire this mess which existed for so many years was cleared, and sadly he died actually in the war of Gallipoli. And then that year, nobody got the Nobel Prize for physics, uh, and which everybody thought, everybody was sure, physics community, that he will get this Nobel Prize. Uh, but then, so people were dealing now, around this time, people were dealing with the biggest crisis in physics, the wave particle paradox, which embarrassed scientists at the time. So the questions people were asking, that at this period of, so trust me, we can see that whenever there is a great inflection point, when there is a phase transition, whether it is in the knowledge or something radical is happening, then the society undergo a very big mass actually. So physics, so how to reconcile? So that was a time when we were transiting actually from classical physics and entering into the quantum world. So how to reconcile wave and a quantum particle, a kind of little bullet at the time? How could both possibly be true? How to deny insights of are Young and Maxwell's are true, or Planck's and Einstein's they are true? For a long while, physicists had to live with the uncomfortable paradox of wave particle duality. People just had to, it came to that level that physicists had to hang on to this experience by skin of their intellectual teeth, even if they could not make any sense of it. Actually, many seems to have done so by rather cowardly tactics of averting their gaze into the scientific conferences. So scientific conferences, they were, all these giants were, not able to answer these questions by probably PhD students. And then we know that component scattering further solidified the quantum theory. And finally, 1 year later, wave particle story had happy ending thanks to the Prince de Broglie. He was actually a prince. So he sent a proposal. It was a part of his PhD thesis, and he said that okay, well, you are fighting, and but I am a young PhD student. I think that these particles can have both particle and these things can have both particle and wave character. And that time his PhD thesis was, people were like, in France, they were skepticism, people, all old people, they put his thesis at one side. And finally it was, they consulted actually Albert Einstein, that what to do with this radical theory which he is proposing. Then Einstein looked at his his PhD thesis, and then he said that this young guy is right actually. So his PhD thesis was permitted, and he was awarded PhD degree only when uh, Albert Einstein had certified that there is nothing wrong uh, with this proposal of P is equal to mv, and assigning lambda to the particles, and then we could calculate uh, for the we have this accelerating voltage for electrons, and if once we know in kilovolt, like, so when we can then we could assign actually, that was the birth of the electron microscopy. So for example, for 200 kilo electron volt, we could assign the wavelength of 2.7 picometer. You can compare it with now small lambda of for X-ray, copper K alpha around 1.54. Now, 100 years back exactly, that's why we are having this meeting. In 1925 and 26, finally the light of quantum physics dawns and removes the centuries of darkness and the sadness. So that was a foundation of the modern quantum theory. So there were two men which stood out here. One was basically the German theorist Werner Heisenberg, and Austrian physicist Schrodinger. So this is a photograph, famous photograph, we have all seen hundreds of times. So just to make it more memorable, I am showing it one more time to you. So that was Solvay conference in 1927. So then this quantum physics, the modern quantum physics was, then that was a, now let's close the first part, that this quantum theory had a success. The theory part had success based on earlier some experimental observations. We have seen all that, and but now it was a free run actually. It was like a floodgate opening in the scientific community. One after another, different research groups started correlating, because that was, now it was easy. Now it was, knowledge, because everything was, mass was clear. So then there was so much of clarity 1925 year onwards, that people started uh, drawing the fruit of the quantum physics actually into the applications. And lot of scientific growth, as we see happen, because in last 100 years, 1925 to 2025, thanks to this, because of this sunrise of quantum physics. So now we know that two groups, one American and one British, Davison German and Thomas and Reed, they independently carried out these experiments, where they proved that electrons can behave like waves. So father got Nobel Prize. The J.J. Thomson got Nobel Prize for proving that electrons are particle, and son got for proving that these are waves. So this was again solidifications of idea in the quantum theory. And then this slide shows that how we had, so this basically slide may sound very trivial to you actually, because you might have seen it so many times, and but in this slide is hidden so many inventions and experimental techniques, and which basically so many spectroscopy techniques, so many microscopy techniques, whatever we see in physics labs actually came out of this concept of atom far away from the plum pudding model, and the concept of nucleus, concept of electrons orbiting in a definite discrete energy levels. So then concept of the band theory came. Remember, the band theory was not there. So then we had clear categorization between metals, semiconductors, and insulators, and then that was then we got the age of lasers, right? And remember, I forgot to add the invention by Professor C.V. Raman in 1928, where he discovered the inelastic scattering, and which explained uh, the blue color of ocean, and many others. So chemists basically started using this invention, but physicists were still not very convinced because of the uh, very low uh, scattering cross section, which will 1 millionth uh, time. So out of like 1 million or more photons, only one photon will have probability of getting the Raman scattered. So then there was an invention of laser, which was also uh, uh, helped by the quantum mechanics, the fruit of quantum mechanics. And then physicists also started looking at the ultra fast spectroscopy, and when they started looking at the ultra fast spectroscopy, then we started realizing experimental proof of laws of uncertainty, famous law of uncertainty, when because we were able to reduce delta E, which is the uncertainty in the energy. And then when we reduce the energy uncertainty, then the time uncertainty increased. And same thing with the delta X multiplied by delta P. Scientifically, we were able to reduce the delta X, and then we saw that delta P, and all those things were scientifically we saw in laboratories. So this entire spectrum of uh, material science, materials physics evolved. And then that was age of semiconductor physics. And age of semiconductor was kind of like a positive feedback cycle. Why was a positive feedback cycle? Because um, age of semiconductor only gave us more powerful computers, which basically helped our basically which helped actually our ability to make complex models, and then understand, have simulation actually. And then DFT and other all these ab initio techniques came, which where we could understand better the collection of atoms and stuff like that, and more multi-scale modeling started happening. So that was possible indirectly or directly by the quantum physics. Had this not been there, we would not have been sitting at the age of semiconductor physics. Then this concept of interesting concept of, but remember, till this time nobody had seen matter at at that scale. It was all spectroscopically, or we could see, for example, Rutherford scattering could Moni Moni. So then there was a okay. So Rutherford experiment indirectly was able to see that there is an there is we have this a tiny nucleus which is in femtometers in dimensions, but that was indirect observation, right? Because through scattering, particle scattering, electron scattering, uh, uh, we could we could feel that we could get a feeling of dimensions. And also don't forget that X-ray crystallization and the X-ray crystallography. We were able to solve the we knew that atoms are arranged in a periodicity, and we could calculate the periodicity. All these things were there. The crystallography had existed, and we had this fruit of this crystallography in biology also. DNA, don't forget the Watson-Crick model and all these DNA, RNA, and the concept of genetics. Everything came out of this crystallography and everything. But but one thing was still missing. because human mind wanted to see things actually. The notion was atom was there like a rigid ball, even though physicists had purist like physicists had knew that there is nothing such as bonds and bonds and atoms. It's an illusion. A concept of atom itself is the biggest illusion. Physicists knew it, but general public thought that there is, there is a concept of atoms, and we don't even believe in the concept of electrons, protons, and neutrons. We know that we have the quarks and mediated by gluons, which are basically 1 millionth of times smaller in size that of an atom. So they are probably less than a femtometer in size, the quarks. So, but how do you even visualize the molecules? So the quantum one invention from quantum tunneling, which is basically scanning tunneling microscope, for the first time in 1980, 84 or 83, for the first time it showed a finer picture of the atomic world by looking at the um, electron cloud, and the resolution was such that, so resolution was limited also by quantum mechanics. Once long back, almost 10 years back, I was giving an FDP in Pune University Physics Department, and I made this statement that nobody has ever beaten the first record, which was held by STM, because it was limited by quantum physics, the tunneling. People said, "Wow, what are you talking about?" I said, "It is just look at the equations actually." So the chronology of evolution of quantum tunneling is also very interesting. After the Schrodinger equation was published, then Frederick Hund was the first person. He applied Schrodinger equation to a problem that involved tunneling between two classically allowed regions, and so on and so forth. And Mendel Stem and Leontovich discovered tunneling independently 1 year later. Then famous scientists, Fowler and Nerdheim, we know the field emission equation. We still use the equations given by Fowler and Nordheim. So they gave the equation, they consolidate the thermionic emission and field emission both, and then they give this how, so they related actually with the temperature and the work function, right? They were able to relate it with the work function, and that was also thanks to the quantum mechanics. Then 1928, Robert Oppenheimer published papers again on field emission. Then, but largely it was a contribution of Aulo Nodem, which basically gave this concept, early concept. But the word tunneling was not, tunneling effect was not used. They were all talking about penetration or leaking, electron leaking through a barrier, these terms. So the first time this tunneling word was used by none other than Schottky in 1931, a German term. I don't speak German. Wellen Mechanist, whatever tunnel effect. It sounds like okay. So then Frankel, in his textbook in English, for the first time used after German this German word tunnel effect. Then almost 25 years later, Isaki demonstrated the tunneling at the nanometer barrier in semiconductor structures. Then we know that Josephson work on superconductors, and finally in 1981, the IBM scientist Bening and Henrik Rohr developed STM. Now we can actually show in the laboratory. We can demonstrate the quantum tunneling in the laboratory so easily. You just walk into our lab at NCL or any other STM lab, and you can really see the tunneling effect taking place. So basically, for the first time, we were able to show to the common masses that yes, because people really did not believe it, even Einstein had debated. We all know. Uh, so any new radical theory, any radical new transition is always taken by society with a lot of skepticism, because human mind has to be and quantum theory. let me tell you one thing, that classical theory fits into the logical. When we talk about logical, rational brain and rational brain, we glorify rational brain. Let me tell you, it was sometimes our logical and rational brain uh, basically become hindrance to our growth of our ideas, because logic and rational works only based on the data. Like AI, basically it is data hungry, right? The search, all this Grok and ChatGPT search is, you feed wrong data and then you get the wrong, you feed junk and you get the junk out, right? That was a problem. That's a problem with the logical mind. Logical mind, you feed junk and junk will come out. So the creativity anywhere comes out of chaos and irrationality. The most creative people are more irrational, illogical, and chaotic in nature. That is the birth of new science and new art. Logical and rational mind do not necessarily create the greatest things in life. Just trust me on that. So quantum theory was not taken by public because it was non-intuitive. Something because common person will look at the classical objects and absorb their features or phenomena very easily, because we connect our senses connect to that classical word so easily. But the quantum world is not connected to our senses, so human perception, they defy actually the common sense. So it was taken by suspicion and all kinds of things. Even now many people may, general public may see that, oh no, it's all illogical, it's going to change, and earth is still flat, and all kinds of people are still, they still exist in the democratic world. Um, so first time we started feeling the atoms. I won't say that these are the atomic picture, because for me there is nothing such as an atom basically that we don't have. So it's just an electron cloud which we are trying to interact with. So it's basically for example, X-rays don't look at the atoms. The X-rays look at the electron density distribution. Electron microscopy do not show you atoms. Electron microscopy look at the potential distribution actually, right? Optical techniques show you refractive index differences, because that's how uh, the photons get scattered by any inhomogeneity in the dielectric medium actually, so, but these are some pictures, some examples how quantum tunneling was helpful in looking at the finer and finer molecular world for the first time, and it still holds the world record in in terms of the limits of lateral and vertical resolution limits of microscopy. And another, but there was another one mystery which we see in when we do electron microscopy. uh, uh, there was one mystery that when if we calculate that at any given so in electron microscopy we bombard electrons through a slice of material. And now one can ask that at a given time, uh, uh, how many electrons might exist in the material, the slice of the material, a few tens of nanometer thick, and for polymers it can be few hundreds of nanometer thick. So if we do the calculation for 100 kilo electron volt energy electrons, and if we take the velocity of electron to be half of the speed of the light, which it is, so then we realize that if we take the current to be at up to 1 microampere, then around 10 to the power 12 electrons they pass through the sample in 1 second. And if we calculate the distance between, you will be shocked to know that that the distance between the two electrons are separated by a very large distance, which is 0.16 centimeter, almost 1.6 millimeter, which means it is like leaking roof, tap tap, in the rainy season, one drop, then one drop. So which means that there is never more than one electron in the specimen, which is shocking to the, again I will tell you, intuitively it is shocking that how can one electron so, have self diffraction? Can one electron show diffract by itself? Because we intuitive mind does not see, because diffraction interference had been into existence since Thomas Young and Airy and all those giant scientists long back, almost 300 years. But then this single electron diffraction, we never so we see it all the time in electron microscopy. So in 1980s, finally in Hitachi, Japan, this group, I will just show you, Dr. Tonomura showed that he did this experiment actually, where he took one electrode and then basically electron biprism, and he was bombarding one electron at a time. So one electron at a time he was shooting. An electron had electron had a option to follow either uh, to go through this path or this path. It was like it was more like a double slit diffraction. So then ideally there should be two piles here. Electrons should either land, all the electrons should, half of the electrons should land here, or half of the electrons should land here. So but when he looked at over a period of time, so he was bombarding 10 electrons per second, so that is fairly low. When he found when he looked at the screen after long bombardment of slow bombardment of electrons, means slow means I'm not the speed but the rate of electron, 10 electron per second, then he saw something very surprising. And just remember, it's a single electron diffraction. So then he saw one, this is basically slide A is basically 8 electrons. Out of 8 electrons, 1 2 3 4 5 6 7 8 8, so you can see all, they are all distributed everywhere randomly. And then 270 electrons, you can still see a randomness kind of a thing. And for 2000, you can see that now there is a pattern which is emerging. uh, Now once you have 160,000 electrons, now you can see a clear interference patterns where you have bright and dark fringes. That means single electron is not going, so that is basically showing self diffraction. So and it was proven on single photon scattering also. And surprisingly, if you look at, so theoretically it was already given. If you look at I think volume 2 of Feynman lecture series, so theoretically Feynman had already suggested that electron, a single particle can self-refract. So that was another demonstration of quantum nature of the matter, actually, the particles, subatomic particles. And now we come to the last two slides. I think still have 5 minutes. So, and these are two very serious slides, and be ready for hold your heart. Okay, now some serious stuff here. So, what is the future of science? And that is, it's not like speculation. I'm just compiling the concept from these four books. The famous the father of artificial intelligence, Ray Kurzweil, he has written a series of books. He wrote earlier the singularity is near. Now he has written singularity is nearer, actually. So when we will merge with artificial intelligence, and there is another book, City of on Mars, which which questions the ability of humans, which have biologically evolved on this comfortable Earth conditions with the particular oxygen nitrogen ratio, particular gravity, and particular humidity, particular temperature, particular cycles of lunar and solar cycles, which governs our psychology and everything, right, our mood and emotions. So then next book is basically by Michio Kaku, latest book on quantum supremacy. How then he basically how on he and then how physics will be taken forward. He has written a beautiful book, and his previous book also is quite complement to this latest book. So now top unanswered. Now what are the There are many unanswered questions in science, but then I thought I will list that. This was the last slide. In fact, today, just 15 minutes before I listed that, I will just put forward what are the top unanswered questions out of several that may exist out there. So earliest phase of the birth of the current cycle of the universe. Remember, we have no experimental data to validate the models. So we have no experimental data of earliest phase of the birth of the current cycle of the universe. I believe in the cyclicity of the universe. I don't believe in the concept of one birth, one book, and one death, because that is holding scientists back. The our civilization, Sanatan civilization, believes in the cyclicity, and now even physicists believe the cyclicity of universe. Uh, uh, okay, so top physicists say that the current universe basically tells the end of the earlier universe actually. Um, so then that's the first top question, that because there is no data available. Why there is no data? Because there was so much of charge environment that light could not escape from the earliest phase. When the charge bodies started escaping, then consolidating and forming matter, then we had some data available in form of electromagnetic radiation, which our telescopes like Hubble telescope and I think James Webb telescopes are able to, and other sensors are able to look at those entire spectrum. Then earliest phase of origin of life before evolution kicked in. Same problem with the phase origin of life. We really have no idea how the earliest phase of the life would have really survived. And the top question today, that's one of the unanswered question, the nature of human consciousness. How do you define the consciousness actually? I mean, people are scientists do not agree what should be the one definition of consciousness, because our Indic civilization has a very broad definition of chetana, jagruti, or chitta, where we assign consciousness not just to the animate world, but surprisingly to the inanimate world like atoms and molecules. We think that anything which is moving, which is vibrating, has a consciousness. So that's why we say that this universe itself is a conscious universe. The Western thinkers won't assign. They think only the humans. Their definition is very narrow. Actually, the conscious definition is very narrow. They don't even think animals are conscious. They think only humans are conscious, and everybody, all other species are just to serve the. Even women are just to serve the. That was a concept from Middle East. The women, they came out of the rib of Adam and something like that. So that is holding still the scientists back. These two questions, the cyclicity and the concept of the large definition of the broad definition of the consciousness. We believe in this land that consciousness, anything which vibrates, has some amount of consciousness. So that these are some predictions from my side, compiled from these books. Age of human immortality and genetically engineered humans will achieve within 5 to 10 years. There will be technological advance enough that we will reach the immortality. And that is already, I think, last 2 3 weeks back, Ray Kurzweil himself said that he said that within 3 4 years, but I'm just putting it timeline up to 10 years. Humanoids are already, you can see plenty of models already, I think, on humanoids. But humanoids will be with body better than top athletes, mind better, beating both in IQ and, please hold on, EQ also, of best of the humans. So humanoids will be devoid of evolutionary cognitive biases of humans. So see, we humans have almost 40, more than 40 different evolutionary cognitive biases, and all our decisions are will remain always biased. Okay, but humanoids will not have these biases, so they will be more emotionally intelligent actually, right? People think that they will be just machine, they will not have any emotions. Forget it, actually they will have better emotions, than better emotional stability, right? Mass scale redundancy of 99% of the inefficient humans within 5 to 10 years. Interface between biological brain and silicon memories. But the current human brain, so that was a proposal by Ray Kurzweil, but there is a limitation with the current human brain. The speed limit, basically, that if you look at the data transfer of the brain, that is already the data transfer is million times less than actually the silicon speed of silicon. So if the speed is slow of human brain, the how will you interface between silicon and the human brain? So that is a bottleneck. For that we need to have the genetically engineered humans. I'm not talking about ethics and morality here. Ethics and moralities are age dependent. Something which was um, unethical, immoral thousands years back. Now it is ethical and immoral, and now vice versa. Something which were ethical is now unethical. So that debate I am not going. I am as a scientist. I am just focused on science. That is for social scientists to worry. Actually, the ethics and moral. So sharp decline in the human fertility and the affordability of the life, 10 to 20 years, the age of plenty, but insanity. So that is there that people, there will be plenty of things, but there will be wars and all kinds of chaos because unstable human brain. Quantum computers will become commonplace in 15 to 20 years, probably earlier. Humanoids will be capable of leaving the solar system in cold and dark space. Once we have this answer to the like plasma physics will be able to will be will have then only we will have. So that will plasma physics, the fusion research will be commonplace. So that will give us uh, freedom to escape the solar system and enter into the long voyages of but trust me, only humanoids will be the first passengers on these long journeys, because human body is not capable of enduring, because we are evolved on this planet. The Sunita Williams story, and few months her body like crumbled, like a lot of problems within few months only. So forget about long voyages. She was just on the this solar this space station, which is not very far actually. What will happen and to the long voyages? But last lines of I will say that don't forget the universal law of uncertainty. No one can predict the exact future, but yes, we can predict the probability of events with certain degree of error. So despite of centuries of contributions from giants, we hardly know even a small fraction of the mystery of our universe. And I will end my talk with these two quotes. I think I can safely say that no one understands the quantum mechanics by Richard Feynman, and also my own thoughts that today's science can be pseudoscience tomorrow, and today's pseudoscience can be science tomorrow. And I appreciate your focus very much. Thank you for giving me opportunity. I hope you enjoyed this roller coaster drive of thousands of years of human voice from classical physics to quantum physics. Thank you. Yeah, back to Dr. Jain.
Thank you so much, sir, for the enlightening lecture. Now, if anyone has any question, please feel free to ask online as well as offline.
Was I clear in voice and the audio and video were clear, or there was no internet
Yes, sir,
issue?
everything is fine. Yes, sir.
Okay, thank you.
If anyone has any query, please feel free to ask.
Good morning, sir. I have one question.
Sure. Yeah.
What are, sir, basically humanoids? In one slide, you showed that they will leave the solar system.
Humanoids are basically the robots which have human like capacity. You can look at some companies, like there is a figure 3 model by one company, which there is a company which says that the humanoids will be as common as iPhones in next 3 years, at least in US. So humanoids are basically like your glorified house help. So they will be able to do all the tasks like robots which have human capabilities. So you can dig more deeper. Yeah, there is plenty of information on humanoids. Yeah. Any other question? Yeah.
Okay, thank you so much, sir. Thank you so much to spare some time for us. We had a great lecture with you. So thank you again for being a part on this Quantum Day and sharing your knowledge with us. So now we have some offline activities lined up. So we can. Now I would like to. Now I would like to invite our head of department, Dr. KP Mishra sir, to share his thoughts. Sir, please.
Thank you, Dr. Pankaj, for such an enlightening talk. It's always a great pleasure to hear your thoughts on different aspects of physics. So, I was there during the complete lecture and I thoroughly enjoyed your lecture. So, thank you for sparing your time and giving
Thank
your
you. I
valuable
hope it was
thoughts on this
not too deep.
great occasion, the word Quantum Day. Yes, sir, please.
I hope it was not too depressing or. I mean, we are realists. So
Okay.
I hope it was enjoying. It was not too deep and yeah.
Yes, so very beautifully corroborated. The ideas starting from our ancient Vedic science, starting from Kanad, Kan, Anu, Parmanu, and then corroborating them with our very modern physics. That is, I mean, you ended up with artificial intelligence and then discussing about scanning, tunneling, microscopy, and then finally your final one particular phrase I picked up, the age of plenty but insanity. So as the more information is being gathered, at the same time insanity is also increasing. So that aspect also we all need to look at. So for the students, thank you all for spending your time with such a great scholar, Dr. Pankaj Podar. And a very special reason behind this celebration of World Quantum Day on 14th of April. So if you see the quantum term, it was coined by Planck, as was mentioned by Dr. Pankaj also. So it is Planck's constant that is in the, say, basics of your whole quantum mechanics. So Planck's constant, its value is 6.63 into 10 to the power minus 34 joule second. So if you convert it into another unit, so another unit is electron volt into second. So its value will be 4.14 into 10 to the power minus 15 electron volt second. So 4.14. So that is the reason we are celebrating the World Quantum Day on 14th of April. So it has been intentionally done. So that's the reason I thought I should share this information with you all. So thank you all for say hearing such a great scholar, and there are other activities lined up. So thanks to everybody who and thanks to the students also who are going to deliver their talks or their lectures, their discussions and debates during the event. So thank you, Dr. Pankaj, and thanks to everyone. Dr. Deepika, please.
Yes, sir. Now we have some online offline activities, so we can sign off. And regarding the certificates will be provided to all the participants. So thank you all for connecting with us.